So I'm going to do probably just the one problem right now. Just wanted to wrap up this section. We're on 60. So the last handful of problems have been functional equations that involve power series. And don't really need any previous results for this. So this latest one, what I'm going to work on today, is it gives you a power series which you might recognize as a logarithm. It's something like log divided by x, so that it shifts. On number 59, he had actually, this doesn't really help us, but we had looked at this identity, which you were able to prove using like the previous results, 57 basically. But at the end of it, he mentions log, and he does this weird trick to get a log series out of it, or to deduce the power series for log out of it. But I probably still would not have noticed the connection between log and the next question. Anyway, question is, it gives you this power series, show that it satisfies this functional equation. It might be able to just do it directly. I wrote it down the first day, but I kind of got stuck. But so there's a couple ways to see it. One he mentions is to recognize what this function actually is as like a logarithm. So we could do that the easy way to do 60. So we're looking at number 60. The function is 1 plus z squared over 3 plus z to the fourth over, there we go, z to the fourth over 5 plus z to the sixth over 7, etc. We want to show that if you plug in 2z over 1 plus z squared, it's the same as multiplying by 1 plus z squared. So the easy way would be, first of all, show that f of z is, I want to say like negative log 1 minus z over z 2z, something like that, and then show that this function has that property. So let's double check that first of all. It's not this. It's actually like, I think it's log of 1 plus z over 1 minus z, something like that. I think it might be this. One of these. In any case, so what you probably want to do first is figure out what log of 1 minus z is, and then plug in negative z to it, and then when you subtract those from each other, you'll roughly get this. So this is going to be the easy way, showing that it's some sort of log thing, and then showing that that function satisfies this property. So first of all, let me ignore the previous result. He did give us the power series for log for negative log of 1 minus x in the previous question, but I'm going to just start from scratch with that. I think we might actually want to have a negative here out front as well. It makes it a little easier. So like here, if I differentiate this, we get negative of 1 over 1 minus c, and that negative floating around is kind of annoying me. So let's put a negative here. If this was f0, if this is the original function of z, then its derivative is still negative, and then, actually, I guess it's not, is it? So when you take 1 over this stuff and then you multiply by the derivative of the inside, you get a negative popping out. So this guy's derivative is actually this. And then the second derivative is since this is 1 minus z to the negative 1, by the chain rule, there's another negative being multiplied. So you're basically just getting this to the 2. You're basically just getting this squared for its derivative. You get negative 1 over this squared times a negative 1 again. So it works out to be this. And then the third time you do it, you're starting to see powers coming from here. So here we're going to get 2 over stuff to the 3. In general, you're going to get like 1 minus z to the k in the denominator, but you're going to get k minus 1 factorial upstairs, which is where our Taylor series is going to come from for the original function. This function, okay, can be written like kth derivative at 0 over k factorial, and then we'll give it z minus 0 here to the k. K goes from 0 to infinity. So for us, that's just going to be, looks like you have a k downstairs, right? You just get z to the k over k. So far this is just Calc 2 conversation. We want to make it look like this. I guess we do have a bit of confusion, right? Because I mean, we could certainly start at 0 normally. But our function at 0 gives you 0, okay? So you get 0 over 0 factorial for the first term. And then for the second term, you get a 1. So 1 over 1 times z, okay? So this should really be starting at 1 at this point. Anyway, so it looks like z plus z squared over 2 plus etc. And again, this was just for negative log of 1 minus z is z plus z squared over 2 plus z cubed over 3, etc. Now, if we I guess we could sort of immediately divide by z if you want, but we're also going to look at 1 plus z, which will introduce some alternating stuff, right? If we plug in negative z into this argument, you'd get plus z. And then over here, you're going to get alternating, right? You get negative z plus z squared over 2 minus z cubed over 3, etc. If I then add these together, you'll get this cancellation of the odd ones. But I suppose I actually don't want the odds to cancel, right? The odds are the ones I want to survive. So let's instead subtract these. We could multiply through by the negatives and subtract them. Right? You see what I'm saying? So if we instead take log of 1 plus z minus log of 1 minus z, so I'm going to negate this. It becomes z minus z squared, and then we add it to this, right? So this series would be, I've negated the second row, the second right-hand side, so I get positive z, negative z squared over 2, positive z cubed over 3. When I add them, this is negative and that's positive. So all of the even powers are going to cancel at that point. And you'll have just 2 times z plus z cubed over 3 plus z to the 5th over 5. Yep. Sound good? And that's almost what we wanted. Now if we divide this by 2, and then we also divide by z, you'll be looking at our original function, 1 plus z squared over 3 plus z to the 4 over 5. So someone who's, familiar with Calc 2, familiar with Taylor series, if they remembered their most common Taylor series, like a logarithm, they might recognize that you can sort of adapt a logarithm to fit this function. We just showed it right here. The function that we had in mind originally, maybe I should have called it something else. Let's call it capital F, okay? But capital F is the same as 1 over 2z times log of 1 plus z over 1 minus z, like that. So we just showed that this is true. Now we want to show that for this function in particular, it satisfies this, if I plug in 2z over 1 plus z squared, it's also equal to 1 plus z squared times itself. So show that this happens with this particular log function. Yeah, it looks scary, but it's actually not so bad. So we got 1 over 2, we got basically the reciprocal of this, right? So for the left-hand side, let's just, I guess, leave it alone. Well, we'll divide by 2 in a second. Initially we have a reciprocal of this. So there's a 1 plus z squared over 2z, right? And then I'll divide by 2. So it actually becomes 4z. Then I have a logarithm. And we take 1 plus this mess. Downstairs we have 1 minus that mess. So we'll come back to, we'll simplify that in a moment. I guess we can do it right now. So this is 1 plus z squared over 1 plus z squared plus 2z. So upstairs you're getting 1 plus 2z plus z squared. And then downstairs you're getting, it looks like 1 plus z squared minus 2z. So you're getting 1 minus 2z plus z squared. Okay? That's z plus 1 squared over z minus 1 squared. I don't know why I'm writing it like that, but the argument inside is 1 square. And since it's a logarithm, you can pull this 2 down, right? So maybe I'll do that right now. You can pull the 2 out and it cancels with a 4 and it gives you 1 plus z squared over 2z log of 1. Well, let's go ahead and do this. I'll write it as oh, it was 1 minus z, wasn't it? I see. That doesn't actually matter, though. You can write this, you could have initially written this either way, right? I could have changed the order here. Since it's z minus 1 squared, I could change the order to 1 minus z. So I'm going to do that. Same thing, okay? I should have done it up here. But yeah, this was actually 1 minus z squared, technically. But it doesn't really matter because it's a square. Okay? And the right-hand side is 1 plus z squared times our original function, which is this mess. So divide it by 2z and put a log of 1 plus z, 1 minus z. And hey, what do you know? That looks kind of familiar. End of proof. So that was the easy way to do number 60. Now another way to do it is to just do it directly. But to do that, it involves a negative binomial on this guy. So basically what we're going to do is, the right-hand side is easy enough, right? You just get this series plus z squared times this series kind of shifts it. So the right-hand side is easy to look at. The left-hand side, 2z is fine, right? You get 2 squared z squared, 2 to the 4, z to the 4, etc. That's the numerator. But the denominator, you're getting this stuff to the negative 2, right? Yeah, like this stuff to the negative 2, this stuff to the negative 4, this stuff to the negative 6, a bunch of times, right? So you want to be able to expand something of this form. Actually, I should say negative 2k, but anyway, you get the idea. So it's a binomial theorem with a negative coefficient. So we can just cite that result, of course, but it's something like, if we write a few of them down, you'll probably see what it is. Right. Let's just look at the case of like Taylor series for the geometric series, which is similar to what we were doing up here with derivatives. So like if you had this, you're aware that it's if it was 1 over 1 minus x, you just get 1 plus x squared, etc. This case, you get 1 minus x plus x squared. Maybe the negative is not really the point. That might even be just confusing the issue. But the point is you get this, right? So we get an alternating series with a bunch of x to the k's, and we start at 0, and we go on. We get an infinite series, is also part of the point. Usually if this was a positive power, of course, if it was like a positive integer, you just get a finite list. You know, it's of order n, say. If we differentiate this, we're getting a negative. That's probably why it was nicer. It's usually, it's more common to look at this instead, you know? So we don't have to deal with the negative signs. But again, we take a derivative, we remember the chain rule. Here you're just going to get no coefficient. That doesn't sound right. Yeah, that's true. So here you don't get an extra coefficient, you just get the powers. So on the right hand side, if we differentiate, we get k x to the k minus 1, starting from 0, right? So if we re-index, we could write it as k plus 1 x to the k, is usually what we do. And then we could still start at 0, we don't lose anything, because that first term, the derivative was 0, it goes away. So here's a formula for just this one. If you do it again, you're going to see a 2 popping out on the left-hand side, so you're starting to see that we need to divide by a factorial. Like if you do this again, then there'll be a 2 over here from that power, right? It'd be negative 2 times this times negative 1 from the chain rule. So there's actually a 2 sitting here. But you can see it's actually going to be a factorial in the long run. If we do this like k times, it'll be 2 times 3 times 4, however many, well, 1 fewer than the power of the derivative that you're looking at. On the right-hand side, we now get a second term. So when we re-index, it's going to look something like this. Okay, so this is how I sort of reteach myself these negative powers of binomial coefficients. It's a form that kind of looks like this, right? And there's also this extra factorial. So in general, I would say if we had to go like negative n, we're going to get something like 1 over n minus 1 factorial, and then we have a sum, and it's k plus that number again. That's the largest power that you get. K plus n minus 1, k plus n minus 2, all the way down to just, well, it seems like you're stopping early, right? We didn't actually include a k here. So I'll just write k plus 1 for now. But if we were going to write a nice formula for this, we're dividing by k factorial, right? It's this formula for this stuff is, here's your first term, so it's this factorial divided by k factorial and divided by this factorial. So it's effectively this. You could put a k here, or you could put an n minus 1 here. Not sure which is more useful to us. But they're both true, okay? So that's how you handle a negative binomial coefficient. For ours, we're going to be dealing with something that looks like 1 plus z squared to the negative n, say. So a couple things are going to happen. First of all, your x became negative z squared. That's about it. So let's say this is v going from 0 to infinity. What we said was, never mind the negative sign, we get n plus the value minus 1. So you could go n plus the value minus 1, and then downstairs we'd write like n minus 1, say. And then instead of x, I have some alternating business, and we have z squared. So that's one way you could expand. I mean, that's a series representation for this power, okay? We're actually going to use 2n. So ours is going to look, okay, I'm going to put a 2 here instead. And we're going to have a 2 here and a 2 here. Okay, and that gets us prepared to start talking about this function. So we were given, so 60 says, given the function, starts at 1, right? Yeah, 1 plus a bunch of, it's a sum. So 1 plus z squared over 3 plus z to the 4 over 5, etc. We want to show that when you plug in 2z over 1 plus z squared, it's the same thing as when you just scale it by 1 plus z squared. The left-hand side is what I'm trying to address with this comment, okay? So if I plugged in this argument to the left-hand side, let's see what it would look like. It'll be 1 plus, I mean, I could just write down the series, right? But you get a third of this stuff plus a fifth of this stuff, etc. Whereas on the right hand side, you get 1 plus z squared times this. So I'll just kind of blindly write that for right now. Now this this right-hand side, we've got a 1, and then we have like 1z squared plus a third z squared. So the right-hand side is 1 plus, we could do 1 plus a third z squared. And, you know, a fifth z to the 4 plus a third z to the 4. Continues like that. I suppose if you wanted to, you could write it as the sum of 1 over 2n minus 1 plus 1 over 2n plus 1. And then we have an even power here. I wanted to say 2n probably. Yeah, it's in between the two. See that? So that's our right-hand side. And, well, 1 plus this, okay? I skipped the 0 case. That's our right-hand side. And now we're just going to figure out what this formula would be. The numerator is easy, but the denominator is, that's why I brought this up, okay? Might have been smarter to use like a K or something over here. Yeah, that's all right. We'll keep going with it. So this left-hand side, I've got 1 plus the sum as n goes from 1 onward, right? And then what we have is this number. Yep. Then you've got, well, on top you've got 2 to the 2n, right? So it's like 2 squared to the n. Does that make sense? So 2 to the 2n, and then we've got a z to the 2n as well. And then we've got the part that I talked about up there. So let's write it like this: 1 plus z squared to the negative 2n. So we have a formula for this. It's this thing on the right-hand side up top. Yep. Hey there, Cicatrilo. I'm actually proving number 60 here. But yeah, it's a functional equation. And I just got done showing it an easier way. Like the easy way is to recognize the function is basically this. So first I showed that the function is, this function is that 1 over 2z log of 1 plus z, 1 minus z, and then you can just show it using a logarithm. So it's easier to show it with log properties. But now I'm going back and saying, well, if you didn't know a power series for a logarithm, how could you handle this? And you could just do it directly. It's a little bit painful, but not too bad. It's going to involve one little trick coming up, but we're about halfway through. Oh, nice. Yeah, 55. Must have done that last week. This week has been, I don't know, a bit rough. It took me longer than it should have. But today we're just going to do number 60. I'm going to keep it simple today. So his answer for 60 is actually, so he just says, well, if you recognize it's this function, it's straightforward. So that was one thing. But if you don't do it that way, you're going to then end up doing this. You're going to equate both sides, and you're going to equate the coefficients in both series, and you get this. And I was kind of stumped on that for a little while, but I see what he did. He didn't explain this one little trick that he has to do to get this to pop out. Because on my series, what we just wrote down, this is not the right-hand side. There's really clearly two different... on the right-hand side, I guess, did I write it here? Yeah, it's right there. I sort of wrote it here. Yeah, it's right here. It's right here. So these are your coefficients. It's not one of these, it's actually two of these. So he did some little trick there. He basically cut this in half, in a sense. But I'll see if I remember it in a moment. Yeah. Yeah, that was another thing. I was stuck on it. When I even the simple answer I was stuck on last week, but then Stucky gave me a hint. All right, let's see if I can survive this. So we're absolutely here, and then we have this chunk. This is replacing this part. So what I want to just do is equate the coefficient of a particular, a particular value of n, say. So say we're looking at the nth one. On the right-hand side, we'll have this. So I'm trying to show that that these series are equal, first of all. But to do that, we'll just show that the coefficients are equal. So like the nth term, it's kind of a weird way to phrase this, but anyway, the nth term, this is a coefficient on our right-hand side of z to the 2n. So I'm equating the coefficients of z to the 2n. On the left, here's z to the 2n. So part of it is this. And then there's this chunk, which we need to use a binomial theorem expansion for. So part of it is this series. So I'm going to go ahead and write that here. Well, okay. For one thing, I don't think it goes on forever. All right, let me just write this, I guess. Yeah. You see what I'm doing? I'm screwing this up already. There's a problem here. There's a z to the 2n here, and there's a z to the 2v here. That's part of the issue. So yeah, this formula is going to be slightly wrong. So on the left-hand side, I should have just written this first. Damn it. But the point is, yeah, what am I going to do with these guys? Yeah, they're changing. Damn it. All right, sorry, forget about this. We'll come back to this in a second. Left-hand side, coefficients of z to the 2n is what I'm after. What I'm saying is you've got z to the 2v here, right? And you've also got z to the 2n. So I'm gonna add that, but now I've just kind of confused the issue, right? I need to call this one thing. So never mind. Let's start over. Let's call this k, 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 k. All right. It's the sum. It's the same series that we had on the left. I haven't changed it. 1 plus this. Um, this is a k, okay? Now I'm saying I want to take the coefficient of z to the 2n. So I only want the particular terms where this power is 2n. I want 2n to be 2v plus 2k. In other words, n is v plus k, right? If you do that, if you focus only on those coefficients, you're not going to have an infinite sum anymore. You're going to have, like, you're taking strips. So we have a two-dimensional sum here, one off in the k direction and one off in the v direction, right? As you go from 1 to infinity, and maybe v goes from 0 to infinity. But anyway, we're going to be taking strips of them. We're letting the sum equal n. So I guess you're getting v is like n minus k. So you're getting strips of them like this. For a fixed n, we just, right? So we do get a finite list of points. I guess we can stop at 1 for the k. But my point is, you are letting v go from 0 to actually n minus k, right? Should it be n? No, v should be n. Something's weird about this. But you get my point, is that it's a finite sum. And then we can go back and change this. I'm gonna use this. I'm gonna substitute this for n to replace one of these guys. Which one to do? I guess n. I guess we'll replace v. We'll probably replace v with like n minus k. So let's look again at the same series. I'm gonna keep. I guess I want to keep k. Yeah, I'm gonna try to change v. So what's going on here? K goes from, for a particular value of n, well, k in general goes from 1 to infinity. Oh, I see. I pictured it wrong, didn't I? This would be the thing that was stopping at 1. So it'd be going down to here. So yeah, v would start at 0 and it would stop at n, right? Or I guess n minus 1. That's confusing. Yeah. Yep. Yeah, you can do it that way. Well, I don't know if it's a single sum, but yes, it's a sum over these strips, over these diagonals. So yeah, it's the sum of the strips, sums. But yep. Yeah, so all I'm going to need to do is this. I don't know why I'm kind of hung up on it. I suppose we could also change the order. Of course, I want n to survive, so let's put the series for n outside. I'll have a series for k, which I did not get rid of. So these are still there. And then this number became, I'm going to replace this v. So we'll get 2k, I'll just write it down, 2k plus v. And then downstairs we had 2k minus 1, which I guess is staying the same. Then I got this alternating business. So this is still there, but it's become a little bit nicer. what is v? N minus k. So we've still got this and z to the 2n is what you're looking at there. So this is n. This is probably no longer infinite, right? Like you're going to get values. So we've got a fixed n, right? Say you have a fixed n as like 10 or something. Once this k value gets above that, this is 0. This no longer makes sense once k is larger than pretty much n. Once you get to, well, I guess it depends on what the numerator here is. The numerator looks like n plus k minus 1. So let me write this a little more legibly and it'll make more sense. N is still an infinite sum. N is going, I guess, from effectively 0, but I was going to do just 1 onward and put a 1 plus out front. But we can put a 0 here if you want. That's not so important. Well, you know what? We'll do it this way. 1 plus, we'll say 1 on. But this is actually a finite sum, I believe. This k value. I'll see where it stops in a second. This part's fine. So let's go ahead and complete this. This upstairs in your binomial coefficient looks like n plus k minus 1. And then downstairs, it's 2k minus 1, but I don't actually want it to look like that. I should have gone with the other. Let me see what he said real quick. Yeah, you see how he's got the other form of it. He's not using, well, down here he is. Yeah, down here he is. Maybe I should leave it alone. You see how this almost matches up with what we've got? Anyway. Yeah, his answer is a bit much. So he he uses this fact, which I would not have ever known, but he basically replaces our left-hand side part of it with this. So he's able to show that this is equal because he knows that this is true, and he used some previous result. But I haven't got there yet, so I'm still just trying to show you that this is what we're going to get. Right? So we're almost there. We've got the alternating bit with the, I didn't write it down, but we've got the alternating bit. We've got, of course, the 2 to the 2k. We've got the 2k plus 1. So we have all this chunk. This doesn't quite match up yet, but also the right-hand side is wrong for us, right? The right-hand side for us is this plus 1 over 2n minus 1. Yeah, I should probably take a screenshot of this and explain what's going on. Let me see. I'll pause real quick and do that. Yeah, give me a sec. Oops. Oh no, where'd my screenshots go? That's weird. In documents or something? Let's see. Where are these going? Save to. Okay, I see. All right. Let's call this 60. What are we doing here? There it is. Let's rotate this and export it. Hopefully you can view this now. Okay, yeah, I should probably have cleaned this up a bit. Damn it. Let's do that. Whatever. Oh, wrong button. There we go. That's what I meant to do. All right, here we go. All right, let me add this to your bonk, 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 bonk. Yeah, sorry. So yeah, I'm trying to explain those second two lines, those second two equations. And yeah, for one thing, starts at 1, k ends at, k is n minus v, right? So once, once v equals n, it should stop, right? Why am I having such trouble thinking about this? Or you could just look at this as well, right? There's a point where it stops making sense. V could be as small as 0, so k can't be larger than n. There you go. This still doesn't, well, if k was n, you get 2n minus 1, 2n minus 1. Yeah, there you go. See what I'm saying? If k is n, you don't need to consider anything larger than that. What if it's n plus 1? Don't I get 2n over... See how downstairs it's larger than that? It's 2n plus 1. It's bigger than just 2n. Indeed. So downstairs it's increasing faster. The point is, this can stop at n. And I got that because, like, v could be 0. V goes from 0 upward. So k has a max of n. For any fixed n, you're getting a strip here. And the k value goes from, well, we said 1, but basically just goes from 0 or 1 up to n. So yeah, that is a finite sum on the inside here. So okay, so here's the deal. We're basically, I think, ready to move on. This chunk inside is the coefficient on the left-hand side. That's what we've seen. This is supposed to be equal to this stuff, 1 over 2n minus 1 plus 1 over 2n plus 1. And I would have gotten stuck there completely, but if you look at what he writes like after this, I guess like if you multiply by 2n plus 1 on that equation, he has that it effectively says, how do I phrase this? He kind of cut this in half. He acted like he does the sort of usual thing with this binomial coefficient. What is it? It's like nr is the same as n minus 1r plus n minus 1r minus 1, right? So if you replace this with like 2n plus k over 2k. I wonder if I'm botching this. Minus n plus k minus 1 over 2k. You'll get this guy. And that is 2n plus 1 and 2n minus 1. We're going to have to do some fidgeting still with the n value, but you'll see like in the smaller case, I mean, I guess another way to phrase it is in the larger case, you'll go to n plus 1. And in the smaller case, I was just mentioning that we stop at n. Otherwise, this stops making sense. Once you plug in k equals n plus 1, this is a 0. If you increased this n value by 1, you'll get this. Yeah, I'm not explaining it super well, but what I'm saying is this already is a sum of two pieces. You're able to split this into two pieces and it matches each of these. But it's kind of easier to see it if you already knew what he said here on that middle equation. It is actually equivalent to what we have. I'm trying to see how right now. 2k minus 1. So yeah, I'm running out of room. Let me come back to that. Let's just talk real quick about what he wrote there. If you take his last line, if you like multiply 2n plus 1 on both sides there, you'll get, in the middle equation, you'll get this sum. K is going from, I can't read it. I should have pulled it up. Where is it? K is going from 0 to n. And then you got the alternating bit, and then you've got 2 to the 2k over 2k plus 1. So here at some point you want to multiply by, I should have just put it on top of this, 2n plus 1. And then you've got this junk. So he's saying that this is true. The first thing I want to do is like, yeah. The first thing I want to do is just show that that's true, based on what he said. So, like, he writes that equation and says that that's what we got, and I didn't actually verify that yet. I sort of waved my hands and said it's true, but I didn't actually show you exactly why. Well, I gave a big hint. It's this identity. That's all. So he splits this up, and then you're just a little careful with the ends, and you'll see that if you sum those two things in the middle, if you sum this statement, say this is the n plus 1 case. If you add this to the n minus 1 case, you'll get the formula that we have for equating the two coefficients. But anyway, I'm switching gears here. I'm just going to say, is this true? Well, it's true if the third line happens there. If 2n plus 1 over 2k plus 1 of this is equal to n plus k plus 1, 2k plus 1, plus n plus k, 2k plus 1. So yeah, he said, first of all, observe that this is true. Kind of blanking on that. But what I noticed is that if this is true, you can, of course, replace this whole chunk with the right-hand side, right? So this whole chunk is now sum from 0 to n. So we're going to come back to proving that, if I remember. What got left behind was 2 to the 2k, and then we've replaced this stuff with these two guys, okay? That's easy enough. And then the reason this is going to be true is a previous result. If you look at 39, it's almost exactly what we're looking at here. Okay, so we got all that stuff on the left, starts at 0. All this junk on the left, we have this. That's this guy. So part of your series, we already know from 39 is equal to n plus 1, excuse me. And then if you had plugged in n minus 1 instead, if you replace all the n's with n minus 1, you just get a negative sign from right there. So I'm saying this part from 39 is n plus 1. And then this part is going to be the negative of n. We should probably write that out, but it's true. So if you knew that this was true and you replaced n with n minus 1, on the right hand side you'll get n. But you'll also have a negative on one of these sides, so like you'll have the negative of this stuff is equal to n. So when you add them together like this, you're getting just 1. So that's why this is true. It comes from 39. As for why this chunk is true, I mean, I know we can use that identity here, right? We could say, no, luckily there's no induction in this one. I mean, unless you want to prove some stuff from scratch. Is this going to be that identity again? Like, I was going to say, can I use this? Like, this alone would be equal to n plus k, 2k plus 1, plus n plus k, 2k. Damn it, this does not make any sense. I'm forgetting why this is true. He's like, observe this and this. So I was able to confirm that this is true. But I don't quite remember where he gets this from. It was something kind of obvious, though. So yeah, where is this coming from? Why is this true? I think it's obvious, but I didn't split it up. I must have done something like this. It was kind of easy. Damn it. All right, back up. He says, to verify this, observe that this is true, and then apply 39. So what I just showed you a second ago was applying 39. You know, if we knew this, then we know this. I'm going to try to go back in a minute and verify why we care about that. But in the meantime, why is this true again? Is it maybe just obvious if I write it out? It might be. All right, fine. We'll try it, but I don't. So downstairs you'd get, and then this minus that looks like 2k, right? N plus k minus n minus k. It's 2k, right? And then I have this jazz out front. Anyway, I'm trying to see, is this equal to, oh my god. Well, at least the denominators, no, the denominator's not the same. Huh. Yeah, I think this is all I did. And then like over here, we're going to multiply by that missing term. Well, we'll see what happens. So you do get slightly different terms over here. But yeah, so here we get top minus bottom is like n minus k. And then here, top minus bottom is like n minus k minus 1. So to add, I guess, these, I mean, this guy's got, what, 2 extra terms, right? Like this right-hand side looks like n plus k plus 1 over n minus k. Times 2 of two of these, right? Why? Wait, you can't just factor that. Okay. So it's times this plus itself. I guess I meant to say this plus 1 times this. Maybe I'll leave it in this expanded form. If I multiply by 2k plus 1, this will cancel. You're seeing that, right? And if I divide by 2n plus 1, does that help us? Well, I mean, so I'm trying to see, are these equal? Some stuff is canceling. Like if you, like this is gone, this is gone. But let me just rewrite it. So we can divide by this. We can multiply by 2k plus 1 and 2k factorial. Yep, these will be gone. And then if I multiply by n minus k on both sides, you'll be left with, sorry, n minus k factorial on both sides, or whatever, multiply by this on both sides, you'll be left with an n minus k. So we're now asking, is this equal to this junk that I wrote times n minus k? N plus k plus 1 over n minus k plus 1. Like that. So we boiled it down to here, and of course if you distribute this, you're getting n plus k plus 1 plus n minus k, which is 2 n's plus 1. Indeed. So it worked. so, so yeah, evidently this is true. We just confirmed his last statement, and along the way we applied 39. So we saw that if this is true, then middle equation is true. So we're basically done. I just didn't show you exactly how do we get from, because what we had was a sum of two different, like if you look on the right hand side and you write it down directly, you're going to get this as a coefficient. You get 1 plus a third, or a third plus a fifth, or a fifth plus a seventh, right? So the right hand side, my right hand side, looks like this. But his right hand side looks, you see it there? It's 1 over 2n plus 1. It doesn't look exactly right. But then again, our left hand side also doesn't match his left hand side, right? It's off by a little bit. And I'm saying all you got to do is, like, I forget what this is called, Pascal's identity maybe. But it's an identity on, it's a pretty common identity for binomial coefficients. So the way that I saw that he was right, although I don't know why he wrote it like, I wish he had like explained it with one sentence at least. I don't know why he wrote it the way he did. But if you believe him about that being the coefficient, we can sort of work backwards and say, like, if this was true, then you'll get the coefficients that we have. So let me rewrite what he wrote there in the middle there. If we did have that this stuff equals 1 over 2n plus 1, right? I can't read it. Let's see again. K goes from 0 to n, alternating 2 to 2k, right? This junk, 2k plus 1. So he has this, where we like almost have that. Anyway, what I'm about to say is that if you believe this, then you can also get ours. Damn it. My bottom one doesn't look quite right. There's a reason this has been so confusing. I think I should change the bottom, okay? Instead of using 2n minus 1, we could have just used v. Where did I derive it? Here it is. So I used this, but I should have just used the variable k, okay? You could use either form. So when you when you have a binomial coefficient, or when you're using the binomial theorem, but you have a negative exponent, it looks kind of funky. It's this. So I wrote it as just a binomial coefficient, but I grabbed the wrong one, unfortunately. It is this, but it's also this. So instead of putting 2n minus 1 here, I should have put the variable v. Is that fine? That should be obvious that you can do that. If instead of, see what I'm saying? Instead of 2n minus 1, I want to put a v here. All right? So let's make that a v instead. That means down here it's a v, and then down here it's an n minus k. Okay? When I did my substitution instead of a v. So another way to write down what we have, I got here, right? I got k is 1 to n, 2 to the 2k over 2k plus 1. And then I just went the wrong direction with it. Instead of n plus k, well, that part's staying the same. But downstairs, instead of 2k minus 1, I want to write this minus that, basically. So it'll be n minus k is all it is, right? It's v, or in other words, n minus k. I didn't need to wave my hands and be so dramatic about that. Like, this is what we had, and just by basic properties of binomial coefficients, instead of writing 2k minus 1, you can do the top minus 2k minus 1, right? It's symmetric. Binomial coefficients are symmetric. So this is another way to write that coefficient. And then we have the alternating part. And that's about it. So what we have is that this is equal to, like that, right? That's what I got. If you just do it directly, you'll get this also. He says this. And so I was stumped on this for a little while. But if you just if you believe what he says, and then you add it to itself, but with the n decreased by 1, right? So if this is true, then replace n with n minus 1, and you'll get the following, right? K will still start at 0, but we stop at n minus 1. This has a negative sign in it, I guess. So we get this. This doesn't change. But this does. This becomes n plus k minus 1. And downstairs also does. It's n minus k minus 1. And on the right-hand side, I'd have this instead, right? And I'm saying if you add these two together, you'll get mine. Right? And it's obvious that you will because of like binomial properties. So let's just actually, not because of binomial properties, but because of this this Pascal's identity. I think that's what it's called. But yeah, sort of fundamental binomial coefficient properties that you can just add them together like that. Which also, by the way, was an exercise back in, I don't know, days ago. This one. Yeah. This fact. He didn't give it a name, but I'm pretty sure that's sometimes called Pascal's identity. Yeah. So, yeah, if you add these two together, I suppose the issue is that you have a minus sign, right? There's actually not an issue with these indices. That was one thing that popped into my head, is like, what, there's an extra index here. Is that going to screw us up? But no, you can't actually plug in n. Okay, you can plug in n minus 1 down here, and you'll get 0. But you can't plug in n to this. It'll give you -1, and you just get 0 for the overall term, that overall coefficient. So, so you're safe to ignore those indices, that last index. Anyway, point is, if you add these together, you'll get an extra negative sign here. So you're getting k from 0 to n. We do get the same old alternating business, although this one has an extra one, so I'll take care of that. And then you get this same coefficient. And then what you're doing is you're taking this guy, and you're you're not adding, you're subtracting from it this guy. And you probably recognize that. You probably know exactly what to do. But we should be getting the sum of these, which is my right-hand side. And what you are getting is, let's see, if this was n and r, and this is n minus 1, r minus 1, then this is the same as n minus 1 with an r. Oops, not r. n minus k, like that. So this is the same, right? And voila, does that look familiar? That's exactly the series that we had. So I don't know why he was tricksy like this and said that he got, he was like, just equate z to the 2n and you'll get this. Well, he needed this so that he could use his, he needed it in that form so that he could use this thing and apply 39 to make it work, So in order to show in order to actually show that these are equal, he needed it in this form so that he could use this equation and apply 39 and it would be true. But I guess he just saved a sentence of typing by not mentioning that, oh yeah, you're going to get this and you need to recognize that it's this. Okay, so we had this, but it's equal to that. And then you can split the two series apart and you get that statement. And you can work backwards. So that is it for today. I thought this would take half that amount of time, but you know how it is. Thank you all for watching. I'm going to disappear, and you have a fantastic day.